So we're moving on. So this is the second lesson on differentiation, and we're moving on to optimization. So imagine a company invents a new product, sparkling milk. So that's a great idea, isn't it? Fizzy milk. I mean, you're thinking, I could fancy some of that right now, aren't you? But it's not my idea. I can't claim credit for it. It's my niece's idea. She and her friend, when they were like 7 years old, they were discussing stuff. You know how like 7-year-olds discuss stuff that they have no idea what they're talking about. So her and her friend were discussing how it is you get pregnant. Like how does somebody get pregnant? And her friend, with great authority, told her the way that you get pregnant is by drinking sparkling milk. And then they carried on to discuss it, and then you know what happens when you have a baby and all these kind of things. And so, and I thought that was quite good, because you wouldn't accidentally drink fizzy milk. You'd actually have to go out of your way to maybe ask your GP, say, look, I want to have a baby, can you prescribe me some sparkling milk so I can have a baby, or something like that. I thought it's quite a good idea. But anyway, so imagine you decide to invent this product and you decide to sell it. The price you charge is going to affect whether people want to buy it or not. So if you charge too much, maybe a lot of people say, no, it's too expensive, I don't want to buy it. It sounds interesting, but I don't want to buy it. But if you charge too little, then you won't make much profit on each item. And you've got some fixed costs anyway, the transportation costs and the office overheads costs and stuff like that. So you could end up losing money if you don't charge enough. So what a mathematician would do is he would plot a curve. And he would say, look, depending on the price you charge, X, this is the amount of profit you can make. And before the mathematician came in and told you this, you might have been thinking, I'm going to charge £2 for each can of sparkling milk. That way I'll be making quite a lot of profit on each can. But what you realize is, although each can will be making a lot of profit, overall you won't make a lot of profit. You'll only make £200,000 profit. Why? Because loads of people will just be put off by the price. They'll say, look, it sounds interesting, but I'm not going to try it at that price. Equally, you might have been thinking, I'm only going to charge 50p a can. That way, everyone will want to buy it, and then everyone will become hooked on it. And again, that wouldn't work so well, because maybe it costs you, I don't know, 30p a can to make, and then you've got some overheads to pay for as well. So you end up making very, very little profit out of that. But there is some point here where you are maximizing your profit. And maybe here you're at about £1.20 per can. £1.20 per can. And at that point, your profit is brilliant. Yeah. And what you need to do is you need to target that point. Luckily, it's easy to figure out that point because it's the turning point on the curve. So the turning point on a profit curve would be when your profit has maximized. And that's exactly what you'd want to do. So if you're talking about profits, you'd want to maximize them. If you're talking about costs or waste, you'd want to minimize those kind of things. And so that's all called optimization. So that's the topic that we're trying to discuss now, optimization. Now, it's a really tricky topic. It's by far the trickiest topic out of everything that we've learned so far. And because what makes it tricky is that I can't give you a simple set of step 1, step 2, step 3, do this and it will work fine. But I can still give you some guidelines, and those guidelines will really set the question up correctly for you. You'll start doing your working along the right lines, and you should be okay. So here are the guidelines. Start off by deciding what you want to optimize. In the last case, it would be the profit that I wanted to optimize. Write an equation for the thing that you want to optimize. Write an equation for the thing you want to optimize. Now, the step after this is going to be to differentiate it. But we won't be able to do that if our equation is in two variables. What do I mean is in two variables? What does that statement mean? In two variables means that on the right-hand side of the equation, there isn't just X. There's two letters on the right-hand side. There might be X and there might be H on the other side. Or there might be A and there might be B, and both of them are variables on the other side. So if your equation on the right-hand side has two variables, you can't differentiate it. So what do you do in that case? In that case, you name your equation equation 2. And then what you're going to do is find another equation connecting those two variables. And then you're going to make one of the variables the subject, call that equation 1, and then you're going to substitute it into equation 2. So we'll do this on a few examples, and we'll make sure that makes sense. Now what you will have is you'll have an equation for the thing you want to optimize, and it will be in just one variable. So you can differentiate it. So now we're going to try and find the turning point. And to find the turning point, we differentiate it, we make it equal to 0 and solve. Now let's say it was profit that we were trying to maximize. Making it dy by dx equal to 0 and solving gives you a maximum, but it could equally give you a minimum. You wouldn't know. And you don't want to accidentally find the minimum profit, because then your boss is going to sack you and no one's ever going to employ you again. So we need to double check that we found a maximum when we want a maximum rather than a minimum, or a minimum when we want a minimum rather than a maximum. And you know how to do that. You need to differentiate it again and put your solution into d2y by dx squared. If it's negative, then you've got a maximum. If it's positive, then you've got a minimum. And if it's 0, then it's ambiguous. You need to return to gradient before and gradient after. Decide which solution you want to keep. If you want the maximum, keep that maximum solution. And then finally, put the solution back into equation 1 and back into equation 2. Okay, so those are the guidelines. Let's start seeing how they work when we're doing it on an actual question. So this is a bit of a strange question, because this is a very theoretical question and not an actual situation that we can make sense of. So it says x plus y equals 10. Find the minimum value of x squared plus 4y squared. And I'm just going to play with this for a little while. So, all right, let's try it. X plus y equals 10. Let's try 5 and 5. 5 and 5 equals 10. 5 plus 5 equals 10. So 5 squared will be 25 plus 4 times 5 squared. So that's 100. So that's 125. So that's 125. So that's not bad. Find the minimum value of x squared plus. Well, I found 125, which is quite low. I'm quite happy with that answer. You might say, no. You shouldn't have done that. You should have done x is 2 and y is 8. Or I don't know, let's try x is 0 and y is 10. Let's go really extreme. X is 0 and y is 10. So that gives me 0 squared plus 4 times 10 squared. And so that gives me 100 times 4. No, whoa, that's not good. That's even higher. So you can see that as you change x and y, you could get different answers for this. And we want to find the best values to get the minimum value of this. Okay, so let's look at our rules again. Right. Find an equation for the thing you want to optimize. Right. Find an equation for the thing you want to optimize. Well, this is the thing we want to optimize. X squared plus 4y squared. At the moment, that would be called an expression. It wouldn't be called an equation because it's not equal to something. That's easy to fix. Let's call it A equals x squared plus 4y squared. So now I want to optimize, actually minimize A. So find an equation for the thing you want to optimize. So there's my equation for the thing I want to optimize. Okay, lovely. If this equation is in two variables, yes, on the right-hand side of my equation, there's an x, and there's a y. So it is in two variables. Then call it equation 2. So I need to call this equation 2. And then it says, find another equation connecting these two variables. Find another equation connecting x and y. Oh, let's look around. Oh, look, there we go. We found another equation connecting x and y. Make one of these variables the subject. I think I'll make x the subject. X equals 10 minus y. And call that equation 1. Call that equation 1. And then substitute that into equation 2. So what we're going to do is we're going to take this, x equals 10 minus y, and we're going to plonk it into that equation. And so our equation is going to become A equals, we're going to replace the x with 10 minus y, and then squared plus 4y squared, which gives us A equals 100 minus 20y plus y squared plus 4y squared, which gives us A equals 100 minus 20y plus 5y squared. Okay, it says now you have an equation for the thing you want to optimize. Yes, I do, and there's only one variable on the right-hand side, so I will be able to differentiate that. Okay, so differentiate it, make dy by dx equal to 0, and solve. So I'll just move this tab out of the way. And then I'm going to differentiate this, make dy by dx equal to 0, and solve. So differentiate this, dA by dy, because it's in terms of y, I get dA by dy equals, the 100's going to disappear, minus 20 plus 10y. Make dy by dx equal to 0. Make dy by dx equal to 0 equals minus 20 plus 10y. And solve it. 20 equals 10y, y equals 2. Y equals 2. Now I need to check whether y equals 2 is actually going to find a minimum, which is what I'm after. Or maybe it actually finds a maximum, which is not what I'm after. And the way we do that is by doing d2y by dx squared. We know that. So if I differentiate this again, d2y by dx squared is, well, that's going to disappear, and that's going to give me 10. d2y by dx squared equals 0. Now I'm supposed to put y equals 2 into this equation, but you notice this equation is just 10. It's not 10y. There's nowhere for me to put the y in there. Well, that doesn't matter then. That means that when you put y equals 2 into there, it stays as 10. So d2y by dx squared is 10. 10 is obviously positive. Positive means we're talking about a minimum. So it is a minimum. So it is a minimum. Great. So we know y equals 2 does deliver a minimum. Okay, now put our answer back into equation 1 and back into equation 2. So put y is 2 back into this equation here. Okay, so if I put y is 2 into that equation, it gives me x equals 10 minus 2, which is 8. So that gives me x is 8, x equals 8. And then now I'm putting both of these values, y is 2 and x is 8, back into equation 2, back into this equation here. So that gives me x is 8, y is 2. 8 squared is 64, plus 2 squared is 4 times 4 is 16, so that's 80. A equals 80. So A equals 80. Is that smaller than the values I got when I was just experimenting earlier on? Yeah, it is. It is. I got 125 was the smallest value, so that's quite a bit smaller than the values I got before. So A is equal to 80 is the smallest possible value you can get for A in that situation. Okay, but that's a very, very impractical situation. It's a very theoretical situation. I want to come to more practical situations. So a farmer decides to create an enclosed rectangular grazing field by placing 100 meters fencing against an existing wall. Okay, so he's already got this wall. So he's already got this wall. So here's his wall. Okay, so here's his wall. Oh, I didn't want to do that. Okay, so here's his wall. I give up with that. I'm just going, here's his wall. It's a brick wall. Looks like it's been quite badly made. Here's his brick wall. And he's got some field here next to the wall. And what he wants to do is he wants to put up a bit of fencing next to this. So he wants to put up a bit of fencing next to it. So he wants to put up a bit of fencing like this. And he wants to enclose this area, wants to pen off an area. And this area here is going to be, I can't really highlight it in blue now. This area here is going to be the sort of fenced off area where, it's going to be the sort of fenced off area where his sheep can graze happily. Here's his sheep. There's one of them. I know it doesn't look very sheep-like, but I don't really know how to draw sheep. There's a sheep, and there's a wolf here. You can tell it's a wolf because it's got a really big snout, and it's got pointy ears. So there's a wolf, and the wolf will eat them. So that's why he's had to fence them off. Okay, so he's only got 100 meters of fencing, and he's going to put he's going to fence off this area against the wall. What's the greatest possible area he can enclose? So he's a farmer, and he wants to enclose an area. I'm going to redraw this, but I'm just going to draw it from above because from the side it's kind of quite complicated. So from above it's a lot simpler. It's just like this. Here's his fenced off area. This is where they can graze quite happily and safely. And we know that he's only got 100 meters of fencing. So we know he's only got 100 meters. It's got to go all the way around here is 100 meters. Okay, right. What is it we want to optimize? Find the greatest possible area. Find the greatest possible area. So it's the area we want to optimize. Give me an equation for the area that I fenced off. You can use whatever variables you like. I don't care. Just give me an equation for the area. Aaron.
100.
Oh, you're probably going a bit. You're probably overthinking a bit. Just a simple equation for area, like what anyone will give.
XY.
XY. I'm guessing you're saying that this is X and this is Y.
Yeah.
Okay, area is XY. So write an equation for the thing you want to optimize. So Aaron's already done that for us very nicely. And you want to differentiate that, but you can't because it's in two variables. So then we call it equation 2. And we have to find, equation 2. And then we have to find another equation connecting X and Y. So we need to find another equation connecting X and Y. If this is in two variables, we won't be able to differentiate it because if we were to differentiate it, would we call it dA by dx? Or would we call it dA by dy? We wouldn't know what to call it. We wouldn't know how to differentiate it. So we can't differentiate that because there's two variables on the right-hand side. So we need to find another equation that connects X and Y. Give me an equation that connects X and Y. Look at the diagram. Look at the information that we had at the start of the question. And give me another equation connecting X and Y. I'm asking that to Sana.
2x plus 2y equals 100.
Are you sure? Because remember, we've got a wall here, so we don't need to place any fence along the wall. Here, you don't fence along that wall. You only need to fence here.
Okay, so 2x plus y equals 100.
Lovely. So 2x. So 2x plus y equals 100. Make x or y the subject of that. Y equals 100 minus 2x. Call that equation 1 and shove that into here. Shove that into here. Replace that y with 100 minus 2x. So our equation is now going to become a equals x, and then we're going to replace the y with 100 minus 2x. Now we've only got one variable on the right-hand side, so we can differentiate it. Of course, we need to get rid of the brackets first. So that's going to give us area equals 100x minus 2x squared. Then we can differentiate it. dA by dx equals 100 minus 4x. Then we can make dA by dx equal to 0. Optimization is finding the turning points. dA by dx equals 0, which is 100 minus 4x equals 0, which is 4x equals 100, which is x equals 25. But is x equals 25, is that going to refer to a maximum or is it going to refer to a minimum? We need to be sure because he wants the maximum area. And if we've accidentally found the wrong one and the answer we give him leads to the minimum area, when he eventually discovers that it didn't work and it didn't give him the maximum area, he'll be very annoyed with us and he'll come with a shotgun for us because farmers always have shotguns and they shoot people quite effortlessly. So how can we check to see whether we've got a maximum or a minimum? Shimon.
Could you just put it back into the equation and then find out
Oh, what happened to d2y by dx squared? Why are you not using the second derivative? Tell me again, Shimon.
You use d2y and dx squared.
Differentiate this again. So if I differentiate that again, what do I get?
You get minus 4.
d2a by dx squared equals minus 4. Now I'm supposed to be shoving x is 25 into there. If I put x is 25 into that equation, what does it give me as my answer for d2a by dx squared? Still, Jimin.
Sorry, could you repeat that?
I'm supposed to be putting x is 25 into this equation here.
Yep.
If I put an x is 25 into there, what do I get for d2a by dx squared?
You get minus 4.
Yeah, because there's nowhere to put in the 25, it's going to stay as minus 4. And if d2a by dx squared is minus 4, is negative, does that refer to a maximum or a minimum?
Minimum?
Oh no, Jimin, you don't know. Oh gosh, okay. If d2a by dx squared is negative, that means we're talking about a maximum. So we know it's not a minimum, we know it is a maximum. So x is 25 definitely locates a maximum. So x is 25 locates a maximum. How do we then proceed? Right, let's put x is 25 back into here. So that will give us y is 100 minus 50, which is 50. And let's put it back into the original equation that Aaron gave us right at the beginning. Area equals xy. So area equals x times y, which is 25 times 50, which is 1250 meters squared. Okay, so this is the answer that we're going to give our farmer. We're going to say to him, well, you tell me what answer we're going to give him. So the farmer's come up to you and he said, who are Mr. Mathematician Man? I'm trying to do a farmer's accent. It's not going to work out very well. I be wanting to enclose a greatest area possible with 100 meters of fence against this wall. How should I be going about it? What's your answer to him going to be? And you've got to be clear. They're farmers. If you're not clear, they'll mess it up. Good.
Would you say the length of one side would be 50 meters?
Yeah.
And the width would be 25.
Yeah.
So then your final area would be 1,250 meters.
Yeah. I mean, there's a danger here that he's going to think that this side has got to be 50. There's a danger here that he's going to think that side's 50 because you didn't say which side. So say the side parallel to the wall has to be 50. So come out 25 meters from the wall and then go 50 meters across and then go 25 meters back again. And that will give you 1250 meters squared. The farmer said, "Oi there, you strange man. I know some maths myself. I learned that it should be like this." So the farmer says that, well, if he's got 100 meters, he should come out 33 1/3, go across 33 1/3, and then go back in 33 1/3, because that's symmetrical. So that will give him the biggest possible area. He said that that's the biggest possible area. Is he right? Are we worried now? He seems to make more sense than us. Anyone got a view on his idea that he doesn't believe it? Basically, we've given him the answer. He just doesn't believe us. That happens a lot to scientists.
Included the word that you're not gonna use.
Okay, yeah. So you're saying that actually you're saying to the farmer, your thinking might have been correct if you're not going to use all. But what I would do is I would work out for him. I'd say to him, look, why don't we do 33 1/3 times 33 1/3 and work out what area you get? So 100 over 3 times 100 over 3 gives you 111.1. So it gives you 1,111 meters squared as your area. It gives you 1,111 meters squared as your area. That's not as good. That's not as good as ours. Ours is 1250. We beat you. And so stop trying to do maths yourself and let the mathematicians get on with it. And you just get on with rearing your sheep. Okay. Next question. A carpenter has 20 meters of 2x4 wood. So you don't know what 2x4 wood is. No one knows what 2x4 wood is. But basically, whenever you call a carpenter to do something, he'll say, okay, I need to go and get some 2x4 wood. And it's just basically wood, I think. And so he wants to create a prop to lean his extendable ladder against. The prop and the ladder are going to form a right angled triangle. So what they're basically trying to tell us is that this here forms a right angled triangle. So that's a right angled triangle there. Okay. One section of wood will form the triangular base. I can see that on the diagram. There's only one section of wood here. The height of the triangle will be formed by doubling up using two sections together to create a curve. I can kind of see that on the diagram because I can see that there's actually, he's put two bits of wood together here. And so he's obviously screwed them together with some screws to make a nice strong support for the top of his ladder. The ladder is going to form the hypotenuse. Again, I can see that on the diagram. He wants to make the triangle so that the hypotenuse is as short as possible. That's what we want to optimize. We want to optimize the hypotenuse. We want to make h as small as possible. So we're going to optimize h, which is the hypotenuse. H, which is the hypotenuse, which is this length here, h. Okay, right. What sizes should the base and height be, and what length can he then extend the ladder to? Okay, so let's start off with rule 1. Write an equation for the thing that you want to optimize. Write an equation for h, Rajvir.
H squared equals b squared plus a squared. Yeah.
Lovely. And I presume that you're making that b, and then that's going to be a.
Yeah.
Lovely. Okay, perfect. That's Pythagoras' theorem. Very well-known equation, so we know that inside out. Okay, right. Write an equation for the thing you want to optimize. If it's in two variables, yes, you've got two variables on the right-hand side, then we have to call that equation 2. And that means we're going to need another equation. Hold on. That means we're going to need another equation connecting A and B. So we're going to need another equation connecting A and B. Give me another equation connecting A and B. Think about any information we might not have utilized so far that they told us. Think about any information we might not have utilized so far that they told us. Give me another equation connecting A and B. Dhruv.
20 equals 2a plus b.
Lovely. 20 equals 2a plus b, because that length's going to be a, but then you've got a second piece which is another a, so you've got two of those pieces which are length a, and then you've got this piece here which is length b, and they have to come out of a 20-meter strip of wood, and he's insisting on using all of it. Okay, what we'll do is we'll make b the subject of this equation and then bung it into there. So 20 minus 2a equals b, and then we can just shove that into there. So that gives us 20 minus 2a squared plus a squared equals h squared. And so that gives me h squared equals a squared plus 400 minus 80a plus 4a squared. And then that gives us 5a squared minus 80a plus 400 equals h squared. So h is equal to 5a squared minus 80a plus 400 to the power of half. Now we've hit a snag.
Would you mind just re-explaining quickly, like where you got the 2a plus b from? Because I get the 20.
Yeah. Okay.
It's just a bit confusing.
Yeah. Okay. Absolutely right. Well pointed out. Okay. So that was Dhruv. What we knew is that the carpenter had 20 meters of wood. So he had a piece of wood which was 20 meters long. So it was like that. That was his piece of wood. It was 20 meters long. Okay. And what he was going to do was he's going to cut off one piece for this length here. One piece for that length there. So that piece is of length A that he's cut off. Okay. Whatever was left, he wanted it as two separate pieces. Can you see that there's a piece here and another piece here? So he's got two strips here, not just one strip. And he's sort of screwed them together to try and make it stronger. Sometimes you do that with wood. You get two pieces of wood and you join them together, and then that gives you. So what he's got to do is to make these two bits, these two, let's color them in red, these two red bits. So this red bit here and this red bit here. What he's got to do is he's got to take what he's got left here, halve it, and then that's going to be one of the red bits, and then that's going to be the other red bit. So that length there is going to be A, and that length there is going to be A. And sorry, I've mislabeled that length there. That length should have been B. That length should have been B because that's
okay, fine.
Yeah. Okay. Lovely. Good. Okay. Now we've got to here, and we can't differentiate this. Not in AS. We can't differentiate this. We need to get rid of brackets before we can differentiate, and we can't differentiate this. So square rooting both sides ruined everything. We can't differentiate it. So what do we do? Well, one thing to do is say, well, what if we don't square root it? What if we leave it as this? Well, if we leave it as this and we carry on means we differentiate, we make it equal to 0, and we solve, then what we would be doing is we wouldn't be finding the minimum of h, we'd be finding the minimum of h squared. We wouldn't be finding the minimum because our equation is for h squared. So instead of finding the minimum of h, we'd be finding the minimum of h squared. Now you're going to ask me, yeah, but does it make any difference? Surely if you're finding the minimum of h squared, then you're also finding the minimum of h. And so I'm going to turn that back on you, and I'm going to imagine a few different situations. So I'm going to imagine this situation. I'm going to imagine h can be anything between 5 and 10. H can be anything between 5 and 10. So what's the minimum h could be? It's 5. What's the maximum h could be? It's 10. So that's the maximum h, and that's the minimum h. Okay. In this case, what would h squared be? Viren. In this case.
25.
In this case, what would h squared be?
100.
Does the minimum value of h give you the minimum value of h squared? Does the smaller value of h, 5, does it give you the smaller value of h squared? What was your h squared here?
100.
What was your h squared there?
25.
Which is the smaller one?
25.
So does the smaller value of h give you the smaller value of h squared?
No.
Okay, Viren. So, okay, there's 10. When h is 10, what's h squared?
100.
Is that smaller than 25?
No.
Which gives you the smallest value of h squared? Tell me the h squared value. Is it? I'm going to move the slider. The slider is at 5. What's h squared?
25.
Okay, now I'm moving the slider to 6. What's h squared?
36.
Now moving the slider to 8. What's h squared?
64.
And now move it to 10. What's h squared?
100.
Which is the smallest answer you gave me? The smallest value of h squared you gave me?
25.
Where do I need to place the slider to get the smallest value of h
5.
squared? Does 5 give me the smallest value of h squared?
Yeah.
Okay. Let's try a different slider. Let's try a slider between 0 and 15. So if the slider is at 0, what's the slider is supposed to be h. So if h is 0, what is h squared, Rajveer?
0. 225.
I'm at 10.
100.
Where do I need to put the slider to get the minimum value of h squared?
0.
So the minimum value of h does give you the minimum value of h squared. Agreed? I'll do one more just to reinforce it. Just to prove that we're right. The minimum value of h corresponds to the minimum value of h squared. This time my slider is for h, and my h can go from -10 up to 5. This is h again. This is a slider for h. So my slider starts off at -10. What is my value? So h is -10. What is my value of h squared, Chimin?
100.
I'm at -5.
25.
I'm at 0.
0.
I'm at 5.
25.
Which value? Where do I need to put the slider on here to get the minimum value of h squared?
0.
Not at -10.
No, because it equals back 25. No,
-10
sorry, it
gave
equals
you
back to
100, didn't it?
Yep.
Yeah, which is the biggest out of all of the answers. So in this case, the slider being at the lowest value of h doesn't give you the minimum value of h squared. The minimum value of h squared is when the slider is at 0. So what we've established is that when h is minimum, it does not mean h squared is minimum. It did work for the first two. It didn't work for the third one. Why? What was so different about the third one that our lovely rule that when h is the smallest it can be, h squared is the smallest it can be. What caused that rule to collapse in the third one? What did I do differently in the third one that destroyed everything? Hannah.
Did you use a negative?
Yeah, if you go into negative values, then it will break down. That rule will break down. Sure, if we're only talking about positive values, then if you make h bigger, you'll make h squared bigger. But once you've got but h is the hypotenuse of a triangle. H can't be negative. So in our case, we're not worried about h being negative. So in this case, we can just leave it as h. Oh my God, that was a lot of explanation just to say we can leave it as h squared. Okay, so we're going to differentiate this and we're going to minimize h squared instead of minimizing h. Instead of minimizing h, we're going to minimize h squared, which seems weird, but it's fine. It won't make any difference. It'll be all right. Don't worry. Okay, so we're going to differentiate it. dh squared by dA equals 10a minus 80. And then I'm going to make it equal to 0, because when we're optimizing, we make it equal to 0. We find the turning point with when it's 10a minus 80 equals 0. And then that gives you a equals 8. A equals 8 is a turning point, but a turning point could be a maximum, it could be a minimum, and it could be an inflection. How do we know whether we've got the right one? Well, we're going to have to differentiate again. So let's differentiate again. Let's use a different color. d2h squared by dA squared equals 10. 10 is positive. It doesn't matter whether you put in 8 on there or not. It's positive. Positive means we're at a minimum, so we can get rid of that and we can highlight minimum. We can say, yes, we found a minimum. So A is 8 is going to be a minimum. We know it's going to be a minimum. Okay, now let's just put it back into our other things. A is 8 would mean that B is 20 minus 16. B is 4. So A is going to be 8. B is going to be 4. And then a squared plus b squared is 64 plus 16, which is 80. And then square root 80, which is 4 root 5. And so the hypotenuse, the smallest the hypotenuse can be is 4 root 5. The smallest the hypotenuse can be is 4 root 5. And to achieve that, you've got to make it a base of 4 and a height of 8 would be the way to achieve it. Okay, so that was the second question. And that was a lot more like these last two questions have been a lot more like a real life situation. The first one was to do with area of a rectangle. This one is to do with Pythagoras' theorem. Okay, next one. The cost of a 200-kilometer coach journey is made up of 2 elements. The cost of the driver is £40 per hour. Oh, okay. So the driver, he costs 40 quid an hour. What if I want the driver for 2 hours, Sana?
It's £80.
It is £80. You have to pay him £80. What if I want him for, I don't know, 2.5 hours, Aaron?
100
pounds. What if I want him for T hours? What if I want him for T hours? Dhruv?
T times 40.
Yeah. So cost of the driver, I'm going to call the driver's cost D. D is driver's cost. and I'm going to say D equals 40 times T. I just read that statement and it immediately occurred to me. The cost of the fuel depends on how fast you drive. So here's the cost of the fuel. Find an equation for the total cost of the journey in terms of X. Well, that's easy. The total cost of the journey, let's call C the total cost. Total cost. C is the total cost. C equals the driver's cost plus the fuel cost. Easy. C equals driver's cost plus fuel cost. Oh, crap. Find the total cost of the journey in terms of X. Mine isn't in terms of X. Mine's in terms of D and F. And okay, you need to get it in terms of X, which means you're going to need to replace that with something, and you're going to need to replace that with something. Can you do that yourself and then post your answer up on the chat? Can you do it yourself and then post your answer up on the chat for the equation for C, the total cost of the journey? I will help you by drawing a coach for you so that you know what a coach looks like. Driving along the motorway. Where are we going to? 200 kilometers. That's probably to Manchester. Let's have a road sign saying Manchester this way. Hannah, it's not in terms of X yet. You'll still need to get rid of one of your letters, which is not an X. It's good, but it's not in terms of X yet. It has to be in terms of X. On the right-hand side, the only letter you're allowed to use is X. It's good, though. You're going to need to get rid of the T somehow. Come on, guys. Put your hands up. I'll give you a clue. There's something you learn in GCSE maths, and it connects speed and distance and time. You definitely learned it in GCSE maths. That you can use to get rid of the time. Remember, X is the speed. You know X is the speed. You know X is the speed. No. What did you do, Chimin? Yes, thank you, Aaron. Although you could simplify that. Okay. So we know the fuel cost is 100 plus a half x squared. They already told us that. So that's 100 plus a half x squared. And we already worked out a second ago that the driver's cost is 40t equals the total cost. But now we need to get rid of this t. And we know that speed equals distance over time. We know the speed is x. We know the distance is 200 and the time is t. So that tells us that t equals 200 over x. And then we can replace that t with 200 over x. So that tells us c equals 40 times 200 over x plus 100 plus a half x squared. C equals 8,000 over x plus 100 plus a half x squared. Now we've got x is the only letter on the right hand side. So now we can carry on with our normal procedure, which is to differentiate dc by dx equals, let's write that as 8,000 x to the minus 1. That gives us minus 8,000 x to the minus 2 minus 8,000 over x squared. The 100's going to disappear, plus x. Now we're going to find when dc by dx equals 0. That's how we optimize. It equals minus 8,000 over x squared plus x. That gives us 8,000 over x squared equals x. That gives us 8,000 equals x cubed. That gives us x is 20. X, we need to check. What if that's a minimum? What if that's a maximum? We need to check. We were after the minimum cost. So we want the minimum. We don't want the maximum cost. Don't want to make it expensive. Nobody's trying to find the maximum cost of anything. Let's differentiate it again. Let's do d2c by dx squared. So that's minus 8,000 x to the minus 2. So that's going to give us 16,000 over x cubed plus 1 is our d2x by d. Now we need to put in x is 20 into there, which gives us 16,000 over 8,000, which is 2, plus 1 is 3. 3 is positive. Positive means a minimum. So we know it's not a maximum. We know we're minimizing the cost. So x is 20 is a minimum cost. Let's put that back into our equation for c. X is 20 gives us 8,000 over 20 plus a half times 20 squared. So 8,000 over 20 is 400 plus another 100 is 500. That's another 200. So 700. So the total cost of that coast journey is going to be 700 quid. And let's say, I don't know, there's 35 people fit in the coach. So you have to pay £20 each to go to Manchester. Now, if you want to catch a train to Manchester, it's a lot more expensive. So my coach, which I'm offering you seats on that coach, it's a luxury coach, by the way, as in there's seats on it. And there's, well, that's really it. There's seats on it. And I'm offering you £20 a ticket to Manchester. And you need to go to Manchester because that's where you've got a place to go to university. The train there is like £80. What are you going to do? Are you going to use my £20 ticket? Or are you going to waste your £80 on this expensive, lavish train journey? Which would you choose, Aaron?
Use your one.
You sure? It is cheap. No question. Remind me, what did X stand for again?
Speed.
In kilometers per hour. Okay, so I'm going slowly to save fuel costs.
Oh.
What speed am I going at?
20 kilometers per hour.
That's like what? I don't know, 15, 16 miles an hour? To Manchester. It's going to take you 10 hours to get to Manchester on my coach. It'll probably only take you like under an hour on the train. You still want to go on my coach?
No.
No. Look at my coach here. It's driving on the motorway and it's being overtaken by a snail here. So although the maths is right and it works out that that might be the optimum speed, you can't drive at 20 kilometers on a motorway. That's ridiculous. Okay. So that question was talking about, like, you know, speed and distance and time and cost and stuff like that. It was very different from the previous questions. For my birthday, I was given a cone of radius 12 centimeters and height 16 centimeters. I was desperately hoping for a cylinder. So what I've done is I've sawn the top off of my cone and then laid the frustrum that I had left into a cylinder of radius r. So that's how I got it into a cylinder. I had to chop off a bit off the top, and then I had to shave off some of the sides in order to get it into a cylinder. What's the maximum possible of volume of cylinder I can retain? Okay, so let's have a look at this now. Let's draw the cone first of all. So we start off with the cone. So that can be the height of the cone. And then that can be the base of the cone. And so it looks like this. So here's my cone that I started off with. The base radius, they told me, was 12 centimeters. And the height was 16 centimeters. Okay, so they told me the base radius was 12 and the height was 16. What I'm going to do is I'm going to get a cylinder out from inside there. So I'm going to pluck out a cylinder. The rest of the material, apart from this cylinder, is all going to be wasted. I'm just going to retain myself that cylinder from there. And so I'm going to call the radius of my cylinder, I'm going to call that R. And the height of my cylinder, I'm going to call it H. Write an equation for the thing you want to optimize. Well, it's the volume of my cylinder I want to optimize. It's this volume here of this lovely cylinder that I want to optimize. Give me an equation for the volume of my cylinder. Chimin. You know the volume of a cylinder from your GCSE math.
I can't remember, but is it?
Oh, Chimin.
No, hold on. Is it thing?
Okay, Aaron, you're still doing GCSE maths, aren't you?
Yeah.
Tell them what the volume of a cylinder is.
IR squared H.
IR squared H. And promise me you won't be like these lot who forgets basic things from GCSE when you start A-level.
Yeah.
Okay. So can we differentiate this equation, Hannah?
Yeah. No.
Why?
Wait, yeah. Yeah, you can. So just 2R.
You can't differentiate, Hannah.
Oh.
You've got two variables on the right-hand side. You've got R and H. They're both variables. They could both be changed. Those numbers could both be changed to make a bigger, taller cylinder or a thinner cylinder or a fatter cylinder or a shorter cylinder. So R and H are both variables. You can't differentiate any equation where there are two variables on the right-hand side. So what we need to do is we need to find a new equation that connects these two. So we need to find a new equation that connects R and H. And the equation is going to be found in the geometry of our diagram. What do I mean by in the geometry of my diagram? What I'm going to do with my diagram is I'm going to look at this triangle here. I'm going to look at this triangle here. It's a right-angled triangle, sure. It's a right-angled triangle. It looks like this. Its base width is, oh, what did I write there for the width? I've lost it now. I think it was 12, wasn't it? 12, yeah. So its the radius is 12. So this base is 12. And the height was 16. So that's 16. Now what I'm going to do is look for another triangle that's similar to that triangle. And I think I'll use this triangle as being the similar triangle. I'll use, let's try doing it in yellow. Yeah, that comes out. So I'll use this as my similar triangle, this triangle here. And so that triangle is like this. And these two are similar triangles. You can tell they're similar triangles because they've both got a 90 degrees. That angle's got to be the same in both of them because it's exactly the same angle as each other. And if they've got two angles the same, then they must be similar triangles. Now, what is this length here on my diagram? What is this length on my diagram, Rajveer? On the original diagram, on the big diagram, what is that length?
H.
H. And what is this length on my original diagram?
R.
R is actually that length there. And that length there is actually 12.
Oh, 12 minus R.
12 minus R. Okay, now what I'm going to do is use that rule that we use from GCSE maths for similar shapes. What we did was we said, if you have similar shapes, then whatever the multiplier is for the base, you must use the same multiplier for the height. So if you decide to multiply the base by 2, you've got to multiply the height by 2. Otherwise, you won't keep the shape the same. What is the multiplier? The multiplier is 12 minus R over 12, the end of the arrow divided by the beginning of the arrow. The multiplier is H over 16, the end of the arrow divided by the beginning of the arrow. But these have to be the same as each other. They have to be the same as each other. They can't be different. So H over 16 has got to equal 12 minus R over 12. And so that gives me, let's multiply through by 16. So H equals 16 brackets 12 minus R over 12. And we can cancel that down. 4 goes into that 4 times, 4 goes into that 3 times. And so that gives us an equation for H, which we can use to replace the H in here. So now our equation for volume becomes volume equals pi R squared times this equation here. We're going to use that to replace the H times 4 over 3 brackets 12 minus R. 12 minus R. So volume equals 4 over 3 pi R squared brackets 12 minus R. Now I want to differentiate this. So I'm going to multiply it out. Actually, I'm going to do it a different way. I'm going to write volume equals 4 over 3 pi 12 R squared minus R cubed. What I've done is I've left these numbers outside. They're constant numbers, and I've multiplied all the letters. So all the algebra is inside here. These are just constants. So all the variables and the bit. So now I can differentiate it. Now I said to you, you can't differentiate if there are brackets. But the rule is if you just have numbers multiplying outside those brackets, just like constants like 2 or a half or 3/4 or 5 or pi or 4 over 3 pi, you can still differentiate it. So that gives me dv by dr equals 4 over 3 pi. And then I'm just going to differentiate the bit inside the brackets. It's going to give me 24r minus 3r squared. And so that gives me dv by dr equals, I can factorize 3 out from there. And so that's going to give me 4 pi times, and I factorize the 3 out there, so 8r minus r squared. And then I could factorize the r out from there. 0 equals 4 pi r, 8 minus r. And so that gives me r equals 0 or r equals 8. I'm going to ignore r equals 0 because personally, I don't like cylinders with a radius of 0. They kind of annoy me a lot. I see them everywhere I go, these cylinders with radius of 0, and they just infuriate me. Okay, so r equals 8. I need to check that r equals 8 does give me a maximum. So d2v by dr squared. So let's differentiate that again. d2v by dr squared is 4 pi times 8 minus 2r. And then put in r is 8 into there. If you put in r is 8 into there, it's going to give you 8 minus 16, which give you minus 8, times 4 pi, which is going to give you minus 32 pi, which is negative, which means that you are talking about a maximum point. So this is a maximum point. And then now that I've got r is 8, I can put it back into this equation and find the volume. Okay. What did it ask me for? It says, what's the maximum possible, find the equation for the volume, what's the maximum possible volume I can retain? So now we can just put our R back into that equation. R is 8 back into the original equation. Let's put it back into this equation here, 4/3 pi. So we're putting in R is 8, 8 store as X, and then I'm typing in X squared brackets 12 minus X, close brackets, and then I'm timesing it by 4/3, times it by 4/3, but I'm not going to times it by pi. Actually, I can times it by pi, can't I? Times pi, because the calculator will just leave the pi next to it. And so the answer it gives me is that the volume is 1024. Volume is 1024 over 3 pi. So that's the maximum volume I can retain. Okay. Very different from the last question. They've all been very different from each other, the questions. And you can see how there are some things that are the same. Write an equation for the thing you want to optimize. Decide if it's got two variables on the right-hand side. If it has, you can't differentiate it. And you need to find another equation to connect those two variables and then replace one of those variables. And then you can differentiate it, make it equal to 0 and solve. And then check whether it's a maximum or a minimum. And then put your answers back into the earlier equations. Okay, we've got one more, but we've massively overrun. I'm sorry about that. I normally feel very, very guilty when we overrun because I know your parents are waiting outside and the car's getting colder and colder, but I don't feel so guilty when we have. I do feel bad, but I don't feel like